In this exercise, I'd like to run a test on the crankshaft component in this assembly. The shaft is held in place by a couple of bearing components and is connected to a link component with a striker plate. When the striker plate makes contact with the block, there will be a force pushing up on the crankshaft. But how much force will be applied as a result of the interactions in the mechanism? One way to find this out is by running a study in SolidWorks motion simulation. Motion simulation takes into account all of the components in the mechanism and can tell you how much force is being applied, including any inertial force as the crankshaft is rotating, as well as the impact force when the striker plate makes contact with the block. The mechanism is accurately simulated, including the real behavior of the bearing components, along with the physical properties of all the other parts. In this case, the motion simulation tells us the maximum load the crankshaft will see is right around 1,000 pounds of force. Now that we know how much force the crankshaft component will see in its true interaction, I can use Simulation Xpress to analyze the part in a static study. Remember, to analyze this using Simulation Xpress, I can only analyze the part by itself, so I'll open it in its own window. I'll go ahead and launch Simulation Xpress. In the Options section, I want to switch my units to English. Since the study we looked at in the full version of simulation reported 1,000 pounds of force, I'll keep all of the units consistent. I'll leave the default file location where the results will be saved, and click Next to move on and apply a fixture. Xpress wants to know where the crankshaft will be held for the restraint. Now in this case, the part is actually held in place by the bearing components on the ends of the shaft. In the full version of simulation, it would be much more realistic to use something called a bearing support, which accurately represents the interaction of a bearing, which can allow some self-alignment. At the end of this lesson, I'll show you what those results would look like from the full version of simulation. But for now, keep in mind that Xpress has a focus on simplicity and only allows a fixed geometry type of restraint that prevents movement of the face or faces you select in all directions. To select the faces, I'll click Add a Fixture, and I'll select the faces where the bearing components are located. Again, I've used a split line feature on the part to make only the areas where the bearing components are selectable. Once they're selected, I'll click the green check. This is all we need to hold the part, so I'll click Next to move on to applying loads. I'd like to apply a force load. I'll select the cylindrical face that the link component will be connected to. For the load direction, pay attention to the direction the arrows are facing. Since the force will be pushing up on the crankshaft when the striker contacts the plate, I must use a reference plane to specify the direction. So I'll activate Selected Direction option and use the top plane from the feature tree to specify the direction. If the preview arrows still point in the wrong direction, you may have to check the reverse direction box at the bottom of the property manager. For the force value, I'll make sure the units are pounds and enter in the 1,000 pound force value that the motion simulation study told us earlier. I'll click the green check, and since I don't need any more load sets, I'll click Next once more. Now this takes us to the Materials section. I want to run this study for alloy steel. So I'll click Change Material, browse for alloy steel, and click Apply. And close the Materials window. With the materials set, I'll click Next. Xpress now has all of the information it needs to run the analysis. I'll use all of the default settings for the mesh size. And we'll go ahead and run the analysis. When the study finishes running, you can see an animation showing how this crankshaft will deform in the center as a result of the striker making contact with the plate. The animation is the same as I would expect the model to behave. But what about the areas near the bearings? Well, as I mentioned earlier, the fixed restraint type is not ideal for accurately simulating the true interaction of those components. In reality, there would be some off-axis rotation of the crankshaft. In the full version of simulation, I mentioned there was another way to restrain the part using bearing supports. Had we used those instead, we would have seen more accurate results. I'll click Yes to begin viewing the results, and we'll start by looking at the von Mises stress in the model. Here, you can see the highest stress is in the area with the fillet. While a bearing support in the full version of simulation would have resulted in a more realistic behavior, you can still see that both the full version of simulation and Xpress both show that same area on the design experiencing the most stress. While Xpress did provide valuable insight into this design, You must keep in mind that the stress values Xpress reported could vary greatly compared with full simulation in an example such as this, where the fixed restraint type was the only option. In this case, Xpress tells us that the part is seeing about 29,000 psi. This is much lower than the yield strength of the material, which is 90,000 psi. If you look in the task pane, you can see the factor of safety is around 3. The maximum psi is about 1/3 of the material's yield strength, which makes sense. To see how the model is behaving, I can take a look at the displacement results. I'll click on Show Displacement to view the displacement results. Here, I can see how the part is deformed under load. The view you see here is exaggerated over 226 times to clearly see the behavior that's being exhibited. Again, you can see in the task pane that Xpress tells me that I have a factor of safety of just over 3. If this design called for a factor of safety of 4, I can type in 4 and click Show Me to see where the design would have failed. Here, you can see areas in red around the large fillets, as well as where the bearings were restraining the part using the fixed restraint. When you're all finished, click Done Viewing Results to continue with the wizard. And I'll skip the step of generating a report for this exercise. The final step in the wizard lets you optimize the design. We won't go through that here in this exercise, but I urge you to try it yourself and see if you can adjust some of the values to meet a higher factor of safety. Now, throughout this lesson, I threw out some terms you might not have been familiar with, such as bearing supports. But don't worry, the full versions of simulation are actually very user-friendly, and there's a wealth of training available.